Hi everyone, my name is Ezra and I'm going to present our work on multi-agent contracts. This is based on a joint work with Thomas Kesselheim, Michal, Feldman and Paul Duetting. Contract theory studies one of the most fundamental questions in macroeconomics, of how to incentivize people to work. Consider, for example, a website owner that wants to promote his website. To do so, he hires a marketing expert. The marketing expert can take several actions in order to do so. He can promote the website on Google or Facebook, he can increase the exposure or try to find the target audience. All the expert actions have some cost for him, but only contribute to the website owner. The website owner sometimes cannot monitor the actions taken by the expert, but he can observe some implications of the actions taken by the expert, such as the increase in the number of entrances to the website. This is one of the most basic principles in contract theory of the hidden action model. The website owner wants to design a payment scheme that is only based on what he can observe. For example here, on the number of entrances to the website. That on the one hand will incentivize the expert to put in enough effort, but on the other hand will not cost too much. Ostrom described it via the following model, where we have one principal that needs to delegate the execution of a task to one agent. The agent can take one of several actions. Each is associated with a cost and a distribution of the rewards that the principal gets. If the agent takes action A, then he pays a cost of C of A, and the principal receives a reward distributed according to some distribution that depends on action A. So far, the agent has no incentive to take an effort, and therefore will always take the least costly action. To incentivize the agent to exert effort, the principal can commit to a contract that maps outcomes to payments. Or in the case of binary outcomes, where the rewards are either 0 or 1, the contract can be described by a single parameter, alpha, of how much the principal should pay in the case of a reward of 1. So overall, first the principal commits to the contract alpha, then the agent selects an action and pays its cost, then an outcome is realized according to the distribution associated with the chosen action, and then the principal pays the agent according to the outcome and to the committed contract alpha. Note that the payment does not depend on the action, which is a key part of the hidden action model. The second key property is that the payments are always positive and are from the principal to the agent, which is the limited liability principle of the model. The utility of the principal is then 1 minus alpha times the probability of success of the action chosen by the agent. And the agent utility is alpha times the success probability minus the effort cost of the action chosen. The main question is then to characterize the best contract that maximizes the utility of the principal. The algorithmic question is how to find it efficiently. In today's talk, we are going to consider a variant of this problem where we have multiple agents. To focus on the multiple agent setting, we will simplify other aspects of the problem, where we will have binary outcomes, which means that the rewards of the principal are either 0 or 1. We also simplify the action space of the agents, where each agent has a binary action space, which means that it can either exert effort or not. Along the way, we will reveal connections between contracts and combinatorial auctions and to pricing schemes. In our model, there are n agents, which we will denote by 1 to n, and each agent is associated with a cost C of A. The principal success probability is a combinatorial function of the set of agents that exert effort. So if the set S exerts effort, the success probability is f of s. The success probability function is combinatorial, not necessarily additive, and we will consider the hierarchy of complement-free combinatorial functions introduced by Lehmann, and Nissan. A contract is described by a vector of size n, where alpha I denotes the payment in case of success to agent I. The expected utility of the principal under contract alpha, if set S exert effort, is 1 minus the sum of alphas times f of s. And the goal of the principal is to find a vector alpha and a set S to maximize this utility under the constraint that only agents in S exert effort in an equilibrium. The focus of the talk is on complement-free combinatorial functions, also known as subadditive, and on XOS functions, also known as fractionally subadditive. A function is subadditive if for every sets S and T, f of the union is at most the sum of f of s and f of t. A function is fractionally subadditive if for every s and every fractional cover of s described by sets s1 to sk and coefficients a1 to ak, such that for every element j in S, the sum of coefficients of the sets that contain it is at least 1, then it holds that f of s is at most the sum of ai times f of si. It is known that the class of fractionally subadditive functions is a strict subclass of the class of subadditive functions. Back to our model, so the goal of the principal is to incentivize some set of agents S. And to incentivize a set S, the most efficient way to do so is to pay nothing to agents outside of S, and to pay agents in S their cost over their marginal value to the success probability with respect to S. Thus, the problem is equivalent to maximize the following function g, which is f of s times 1 minus the sum for I in S of ci over fi marginal. The problem is that although our success probability function has a very nice structure, such as being monotone and subadditive or XOS or submodular, these properties don't carry on to the function g. The function g is not monotone and can be negative, and for the case of f which is XOS, the corresponding g is not necessarily subadditive and can have very strong non-continuity. Therefore, approaches like local search can lead to really bad local optima. We show in the paper that for the case of XOS f, it is possible to find in polynomial time, using values and demand queries, a constant approximation to the best contract. Our second result is that for the case of subadditive, we show that one cannot get in polynomial number of value and demand queries better than square root n approximation. For submodular, a constant approximation can be achieved using only value queries without demand queries. For the case of additive f, it is NPR to find the best contract, but we present a simple FP task. For the case of XOS, we complement it with a negative result and show that one cannot get better than a constant approximation using polynomial number of value and demand queries. In this talk, we are going to focus on the first result. The multi-agent model has been first studied by Feldman and Nissan, where the key difference is that they were looking at different types of success probability functions. They showed that for general f, it requires exponential number of queries, and then focus on read-once networks and N and or read-one networks. Later, Emek and Feldman studied the case of all read-one networks and series parallel read-one networks. So back to our result. We first present two properties that hold for the problem for XOS functions. The first property is that the cost of the optimal contract are not too high. If we didn't have the square root on the left side, and also not the f of s star in the left side, then we would have gotten an upper bound that holds even beyond XOS. But for XOS, we can bound using the following stronger inequality. Property 2 says that if we have a set S for which all marginals are high enough, then we pay at most half of the reward. These two properties together motivate the use of prices. So let's imagine that we have a stronger version of property 2. Instead of requiring the marginal to be square root 2CF, we only require it to be square root of half CF. Then we can do the following. We first guess the value of f of s star. This can be done up to an arbitrary small multiplicative constant via binary search. Then we can set prices to be square root of cf as s star over 2. We then find a demand set t with respect to the function f and prices p. Then it holds that f of t is at least f of t minus p of t, which is at least f of s star minus p of s star, which is a constant, times f of s star, where the second inequality is by that the t is a demand set, and the last equality is by the definition of the prices and by property 1. Now, if f of t is smaller than f of s star, then you can use property 2 to get that gt is a constant times g of s star. Else, if f is also submodular, which is a stronger requirement than being XOS, then we can remove agents until the f of t is smaller than f of s star, and the marginals can only increase from this process, which will result in a set t that satisfies property 2, and has also a large enough value of f, thus also a large enough value of g. So we have two problems with this algorithm. First, f is not submodular. Second, we want to use the real property 2 and not the convenient version of it. To solve both of these problems, we introduce the following procedure for XOS functions that can select a subset U of an initial set T that has a value between x over 2 and x, and the marginals are at least half as high as the marginal with respect to set T. Whenever it's written an approximate equality or inequality, it means that this adds up to the largest value of one agent. If the function was submodular, one can get approximately x, not between x and x over 2, with at least as large marginal by removing arbitrary agents up to getting to the target value. And what we are going to do next is to do so for XOS by losing constant factors in the marginals and in the target value. The procedure works as follows. We start from u equals t, and each time we remove the agent with the lowest marginal with respect to u over the marginal with respect to t. And we do so until we remove everything. There are two interesting points to consider. The point where we get below x and the point when we get below x over 2. Between these 2 points of time, we know that the sum of marginal with respect to u is x over 2, while by XOS, the sum of marginal with respect to the original t is at most x, which means that at some point the ratio between them must be at least half. If we look at u at this point before we delete this I, we must satisfy both properties 1 and 2. Note that this procedure shows not only the existence, but also how to find one, and it uses only polynomial number of value queries. Now back to fixing the algorithm. We guess f of s star, we calculate the same prices and find the demand set t. Then we use our procedure to find the set u with a target value between f of s star over 32 to f of s star over 64. This set satisfies property 2, thus we get the 64 approximation. For the case of some modular functions, instead of finding a demand set, one can find, using polynomial number of value queries, a set T that is an approximate demand query in the following sense, and all the remaining analysis can be adapted using the approximate demand set. So now, let's prove properties 1 and 2 for XOS functions. For property 1, we can reformulate it as the square of sum of the square root of the cost should be at most f of s star. We know, since the best contract has a positive utility, then the sum of the payments should be at most 1, which is the red inequality. We next use Cauchy-Schwarz by setting xi to be the square root of c over f marginal and yi to be the square root of f marginal. Then we get the property 1 by using the red inequality with the property of XOS that the sum of the marginal is at most f of s star. To show property 2, we can reformulate the condition as c over f marginal is at most f marginal over 2f of s. If we sum over all I in s, we get that this is at most half, again since the sum of marginal is at most f of s. This directly implies that gs is at least f of s over 2. To show the impossibility result for subadditive, we follow the following construction. We start with a symmetric function, a function that depends only on the number of agents exerting effort and not the specific ones. For this function, the best thing to do is to incentivize a single agent and get a very small reward. We then add a specific good set T that is slightly better in terms of f, but is much better in terms of g. This is possible since the structure of f and g can be really different. The modified function is indistinguishable from the original one by value and demand queries. Therefore, an algorithm that finds a good contract that is better than square root 10 approximation must find the hidden set T. A similar construction works for XOS functions, but there the ratio of slopes only allows to lose a constant factor and not square root n, as in the case of subadditive. To summarize, we studied the multi-agent version of the contract design problem and showed that for XOS it is possible to guarantee a constant approximation to the best contract, while for subadditive the best we can offer is square root n. Our work reveals surprising connections to combinatorial auctions, in particular to pricing schemes. Our work opens many follow-up directions, such as closing the gap for some modular functions f. Is it possible to get an f pitas, or similar to the XOS case, can we get at most a constant? For subadditive, what is the best approximation we can achieve? Our work rules out better than square root n approximation, and then n approximation can be achieved trivially. But what is the right approximation for subadditive? Lastly, as our work focused on the complexity of having multiple agents, we simplified other dimensions of the contract design problem, such as having multiple outcomes and multiple actions per agent. Thank you for your attention.